Okay, let's continue our look at the quotient topology. So remember last time I talked this idea about a quotient space. So this is really important in geometry. It's like how we sort of construct certain spaces from other spaces. And so we want to, if we're doing this kind of construction, we want to see how that affects the topology. So we've got this idea of a quotient space where we start off with space and we set up some sort of, it's kind of like setting up an equivalence relation, right? And we're identifying the points in the equivalence relation. So we have the idea of a quotient space, right? And it's given by a quotient map, okay? And we talked a bit about the idea of a subset being saturated with respect to a surjective map. Okay, so that means that if a set intersects the preimage of a certain point, it meets all the preimages. So, for example, if we have, in the situation we had before between RP2, where it's like from S2, where we identify antipodal points. So it's like the equivalence relationship is that some point x is considered equivalent to minus x. And so RP2 is then the set of all the equivalence classes. And so what is a saturated set in S2 with respect to this map? Well, if we have a set like containing some point, it also has to contain all its antipodal points. So that's what a typical saturated set looks like. Okay, so let's have a look at a few examples. So here, we're going from 0, 1 union 2, 3 to 0, 2. We're kind of taking these two unit intervals and we're sticking them together to form a new interval. Okay, and so if you look at that map, we can see it's surjective and continuous, and it's a closed map, right? It'll send any closed set in X to a closed set in 0, 2, our Y. So it's a quotient map, but it's not an open map, right? And we can see that because the interval 2, 3 is an open set in X, in our X here, right? Because there's lots of ways we can think of that. For example, it's 2, 3 is the intersection of X with the interval 1.5 to 3.5. Or another way to think about it is 0, 1 is closed. It's the complement of a closed set that has to be open. But its image is not an open set, right? Because the image of 2, 3 is 1, 2, the closed interval 1, 2. So it's not an open set. So another way we can construct the interval 0, 2 is by let's restrict the domain, right? So let's throw out, so let's replace the closed interval 0, 1 by the half open interval 0, 1. And so we're kind of like concatenating the half open interval with a closed interval. And so as a set, it's a bijection, but it screws up the topology, right? It's a continuous surjective map, but it's not a quotient map. And whereas in the previous one, right, we saw that all saturated open sets get sent to open sets, right? So for example, a saturated open set 0, 1, the closed interval 0, 1 was a open set, but it wasn't a saturated open set because the pre-image of 1 is the points 1 and 2. So any open set, saturated open set, has to contain the points 1 and 2. Okay, this is no longer the case here. So, for example, 2, 3 in this, in example 2, 2, 3 is an open set, but it's a saturated open set, so it should be sent to an open set, but it's not. So this is not a quotient map. So we can, if we concatenate things like that, it's going to screw up the topology. Here's another example. Projection. We know that projection is surjective, continuous, and open. We proved that in the previous homework assignment. So it's a quotient map, but it's not a closed map. And we can see this by looking at these hyperbolas here, right? C equals to the x cross y such that xy equals 1. Okay, that's a closed set, but its image is going to be r minus 0. So projection, going to project here, but we're going to miss the point 0, and that's not a closed set. Okay, now if we let our next example, if we consider C and we add in the origin, so now our set that we're interested in is the hyperbolas plus the origin, where we can, if we restrict pi1 to that, we'll get a map R. So that's going to be a set bijection, but again, it's not going to be a quotient map. And we can see this because 0, 0 is a nice open set in our X here, right? Because in the subspace topology, we can put an open ball around it, and so that's an open set. And it's a saturated open set, but it gets sent to 0, which is not an open set in R. So this shows us, again, another example of a continuous surjective map, which is not a continuous map. So we've got topology now. So idea is, we start off with a topological space, and we have some set A that we've got a surjective map to it. So there's exactly one topology that we can put on A relative which Q is a quotient map, i.e. those are the maps such that the open sets of A are precisely those whose pre-image is an open set in X. Okay, so for example, here we have a map going from the reals to the 3-point set ABC, where P of X is A, if X is positive, B, if X is negative, and C is X is 0. So what's the quotient topology that R puts on the 3-point set by this map here? Well, A is an open set, right? Because the pre-image of A is X greater than 0, which is open in R. B is an open set because X less than 0 is an open set. C is not an open set because X equals 0 is not an open set here. And this will always give us a a topology, right? Because we've got a surjective map. Because we've got a surjective map, A is going to be an open set because the preimage of A is X. The empty set, the preimage of the empty set is the empty set. So the empty set in A are always going to be in the quotient topology. And we know that preimages are handled nicely intersections and unions, because the preimage of a union is going to be the union of the preimages, right? So if the U alphas are open sets in A, we take the union of them, we want that union to be an open set. Well, because of this, each one of these guys is going to be open, and the union of open sets is open. So that works. And also, if we look at the finite intersection of open sets, we want that to be open. Well, that's going to be equal to the intersection of the preimage of these open sets. Well, that's going to be open. The intersection of open sets is going to be open in the topology X. So this is open in the topology A. Okay, and I think that's all I want. Oh, so here are some examples then, just to go over. So here, just sort of putting together all we had. So for example, so we've got this X, we put an equivalence relationship on X, and so the elements of X star are going to be the equivalence classes, and the quotient space is made by identifying those equivalent points. And so a typical open set in the quotient space is a collection of equivalence classes whose union is an open set of the original set X. So for example, we can think of the sphere as the quotient of the unit disk by identifying the boundary of the disk, the unit circle, as a single point. So we kind of like identify that as a single point, say make it the North Pole. And so this is what typical saturated open sets look like. So U is a neighborhood of the disk, and so we've got to include all of the disk for it to be saturated, and then that goes on to a neighborhood of whichever the point that corresponds to that disk boundary. We can do that also with the torus, right? We identify opposite sides of a square. So equivalence relation is we've got singletons, which are the interior of the square, 2-point sets, which are opposite points on the boundary, and then there's a special 4-point set, which is the 4 corners of the square. And so here's what typical saturated open sets look like. So if it's in the interior, it can just be a little disk in A. If it's on the boundary, you've got to have the opposite, a little bit of a neighborhood into the opposite side. And if it's in the corner, you've got to have all 4 corners in your neighborhood. Okay, we'll finish this up on Wednesday.